All right. Do you see my screen?
Yes, we can see your screen.
Excellent. So yeah, thank you for the invitation and thank you for the introduction. I'll try to fit into the time schedule. You will let me know maybe 5 minutes before the end so that I can conclude. Today I will give a talk about sensing using optical microresonators on chip. Resonator such as the ones you see on top of this slide. Sorry, just here's my pointer. Here it is. Okay. And the outline of the talk is the following. So I will first describe shortly what are optical microresonators and why we use them. And then I will go to a few examples of sensing with optical microresonators, mainly an on-chip refractive index cytometer and multiplex gas sensing with polymer microresonators. So to start with the introduction, of course, you probably all know about optical resonators. They come in several different configurations. And maybe the most well-known is a resonator made of two mirrors facing each other, two planar mirrors, and light is reflected by both mirrors. But of course, you might find different configurations such as a spherical mirror, ring mirrors. You can have a rectangular cavity, and of course, all these are free space resonators. You might find as well resonators in guided media, so in optical fibers, if the fibers is arranged in a ring type, or on chip, on waveguides, if directly integrated. And there are, of course, many more different types of resonators. I mentioned two types here. You probably know about photonic crystals. If in a photonic crystal, so in a periodic arrangement of materials with different refractive index, if you have a defect in this periodic arrangement, this will also create a resonator. And over the past decade, there have been a lot of work related to whispering Gary mode resonators made of microspheres, microdisc, or microtoroids. So I will describe a little bit more in details in a few slides, but these resonators benefit from total internal reflection, and light is confined at the periphery of the resonator. So for example, at the equator for a microsphere, and at the periphery of a disc of microtoroids. So several configurations, and for any type of, I don't know if I can remove this. Okay, it's annoying. Anyway, so just end the show. Okay, start again. All right. So there are two key parameters for optical resonators, and these two parameters are related to light confinement. So the first parameter related to spatial light confinement is the model volume, V. So this is basically the volume occupied by the confined optical mode. The second important parameters for microresonators is the quality factor. And the quality factor is so related to the temporal light confinement, because it's basically proportional to the storage time in units of optical period of the light. So it's also called resonator lifetime or photon light time. And these two parameters are really important, because if you want to have a kind of a most efficient resonators, you want to have a high quality factor. Obviously, you do not want to have high losses. So if you have a high quality factor, you have low losses. And you also want to confine the light in space by reducing the model volume. And these are the two reasons why we study micro resonators. So it's quite obvious that if the resonators are small, we reduce the model volume. It's maybe less obvious that by making smaller resonators, we increase the quality factor. Actually, this is due to the fact that the fabrication process, refractive index sensor, reports the ratio time versus the area. We clearly see the two different type of cells. So one which have a broken cytoskeleton, and the one which still have their cytoskeleton. So this is very, very important for biologists, and this can be easily. So in conclusion for this first part, we have here a cell discrimination based on refractive index and deformability. And again, we have a limit of detection of 10 to the minus 5 refractive index unit, and a sensitivity a little bit better than the initial devices that I showed before, so more than 1,000 nanometers per refractive index unit. Going to the second application, I focus on gas sensing, and I take again the same type of fabric cavity, but I inject a polymer into the cavity, and actually this polymer can absorb gas, which is around. And by absorbing this gas, actually two things happens. First of all, the refractive index of the polymer is changing, which induce wavelength shift of the resonance. And another phenomenon appears is by absorbing gas, the polymer will swell, and by swelling, the polymer will deform the microcavity. So the shift in resonance wavelengths that we observe depends on the swelling of the polymer and on the change of the refractive index. So we fabricated a little bit different approach as one we saw before. So we have the fabric cavity, we inject light and collect light with optical fibers, and we inject polymer using reservoirs that by capillarity will flow into our fabric cavity. This is a typical chips fabricated with scanning electron micrographs that you see here and filled with a polymer. So if now we expose, or if we take a typical polymer widely used in microfabrication, PDMS, and we expose it to xylene, you see here the resonance wavelengths versus time when we expose to different concentrations of xylene. So you clearly see that for each concentration, of course, the shift is proportional to the concentration. And this can be reported, wavelength shift versus gas concentration. So typically we have here a sensitivity of 15 picometers per particle per million of xylene. And if we report, if we use different polymers, so now we injected with a slightly different mixture of polymers, PDMS with PDPS, we still exposed to xylene, we see there is a different sensitivity curve. And this is very important because, of course, you can expose the same polymers to different gases, and each coupled polymer and gas will have a specific sensitivity curve. And that's important because, of course, our gas sensor is not specific to a gas. It will absorb any type of gas, but not. But the way it absorbs this gas is different from all gas polymer couple, and this specific signature of gas and polymer couple gives us the specificity if you use in a matrix. So if you use several sensors together. So I will come to this soon. So as you can see here, the sensitivity is reported for different types of gases using in color different types of polymers. So as you see that each polymer gas couple has a different response, different sensitivity, right? So this is very important. And we actually use also whispering gallery mode resonators made of polymer to sense gases. So in this application, the disk is in polymer itself. So we couple light to the disk with a tapered optical fiber, and again, when gas is absorbed by the polymer, by the disk, it will generate a shift in the resonance wavelength, and the sensitivity is a wavelength shift versus the change in concentration. But it depends, of course, on the swelling, so a change in radius of the disk and a change in refractive index. So you see again here spectral shift versus analyte concentrations for different types of gases, valeric acid, water, limonene, toluene, and they are very specific. So you see some sensitivities reported for SU weight. So we use SU weight for fabricating these microcavities, and the limit of detection to a few analytes over here. If we compare the sensitivity of such a whispering gallery mode type gas sensor with the Fabry-Perot cavity that I mentioned before, we see we have more or less an improvement of an order of magnitude in the sensitivity. And this is due to the fact that in the case of the whispering gallery mode cavities, we benefit from the expansion of the change in size of the whole cavity, while for the Fabry-Perot cavity, the expansion is limited by the stiffness of the mirror, so it's a little bit less sensitive. So of course, whispering gallery modes are more sensitive, but as you saw, it's also a little bit more complicated to integrate on chip because you need to use a tapered optical fiber. So again, if you see the selectivity and the disk and the sensitivity of this disk, so sensitivity versus different analytes, you see very specific responses that allows us actually to make an artificial nose. And this is, of course, the purpose of this project, to fabricate, and we do already arrays, to fabricate arrays of sensing units. And these arrays, or each sensing unit, can be functionalized with a different polymer. And by doing this, then we have, when we expose an analyte to these sensors, we will have a different response from each sensing unit. And the correlation of all the responses will provide us information on the composition and the concentration of the analyte. So this is what we call an optical nose. This is an artificial nose using optics as a sensing media. So of course the idea is to have a response with different sensors to different gases, and we have a sensitivity around 10 picometers per ppm with a detection level, a limit of detection to the ppm level, and a noise level at around 5 picometer. So with this, I think I went as fast as I could. I would like to thank the people who did the work. So for the gas sensors, it's a collaboration with Queen's University and University of Montreal. The refractive index sensor is a collaboration with Hôpital Maisonneuve-Rosemont from the University Hospital. And the accelerometer is a collaboration with Canadian Space Agency. So I thank you for your attention, and I will be happy to take questions.
Thank you, Professor, for your wonderful presentation. I'll leave some time here. We'll see if anyone have any questions or comments. You can please go ahead and ask Professor Peter.
Okay, good morning or maybe afternoon in some case. My name is Karol Zidek, and thank you for a very nice talk. I wanted to ask because I noticed that you measured in the IR spectral range, meaning that the ship was around 1550. Is there any special reason why it's not easier to measure in the visible range? Since I mean, the ship would be then there are better spectrometers, or let's say cheaper spectrometers there and everything.
Yes, it's a good question. So the reason is the material we use to fabricate the fabric cavity and actually the whispering gallery mode, well, not in polymer, but in silicon dioxide. But in particular, the fabric cavity is done in silicon, and silicon is transparent at 1 micron and above. On the other hand, 1.5 microns is a telecommunication wavelength, so you have a lot of sources, so it's quite easy and cheap to measure light at this wavelength. So you have very cheap light sources and very cheap detectors at 1.5 microns. So it's not a big deal. I think sometimes, of course, depending on what you want to measure, you might be willing to go to the visible, but well, yes, with silicon, we need to remain in the near infrared region.
Okay, I see. Okay, thank you for your answer.
Thank you.